In section 6.3, we're going to be taking a look at something called Eulers Method. And just as a little aside concerning this person who developed this method, Leonhard Euler, he also has something called Eulers Identity. And I think it's an interesting equation in the sense that you can see right here, it contains the three fundamental operations of addition, multiplication, and exponentiation. And on top of that, it consists of arguably the five most important numbers in math: 0, 1, e, pi, and I. And kind of to emphasize that even more, in 2004 a poll was given to mathematicians and scientists, and they concluded it was the most important formula ever discovered. So we're not going to be using this Eulers identity. We're going to be taking a look at another thing he discovered, something called Eulers Method. So what is Euler's method? Well, Euler's method builds a piecewise linear function that approximates a particular solution to a differential equation. What that essentially means is, for problems such as one like this that we've talked about a little bit before, where it is not a separable differential equation, is there possibly a way where we could approximate the particular solution? And the answer is yes. We're going to use Euler's method, which builds a piecewise linear function, and that we're going to use to approximate our particular solutions to a differential equation. We kind of did this in the last section with slope fields, but we really couldn't find numbers. We were able to visually see what the particular solution would look like to a differential equation, but in this lesson with this Euler's method, we're actually going to be able to approximate the particular solutions to our differential equations. So this method is an example of an algorithm. It's just a set of steps. It's kind of a recipe we're going to follow, and you're always going to do the same steps every time. So I'm going to try to develop this equation for Euler's method, but ultimately, as long as you kind of practice these steps, you'll get better at applying Euler's method. So first thing we gotta kind of start off with is realize that this kind of grayed out curve here I'm saying is the exact particular solution. It's the exact solution curve. So if you were able to separate and integrate and find that particular solution, that would be the graph right here in gray. What we're going to do is use Euler's method to build an approximation of that exact solution curve, because again, we're not going to be able to actually find the original equation. So of course we have to start at the initial condition, our given point, which I'm going to call x sub 0, y sub 0. The next thing we need is to use the differential equation to find the slope at that point. So I'm going to go ahead and put here slope is equal to the derivative dy dx evaluated at, remember this bar is just another way to say evaluate that, at x0, y0, and that'll of course give us the slope. Now, we're trying to build a piecewise linear function to approximate the solution. So we need to increase that point by some step size, which we're going to call a change of x. We want to move over some distance, and every problem is going to be different, but we're going to move over some little change of x, which we're going to call a step. So here, we're going to step over to the point x1. And of course, that would have a y value, and I'm going to call that y1. So this distance right here from x0 to x1 is of course a change of x, which I'll label as delta x in the triangle you see. And the distance from y0 to y1 is going to be of course a change of y, which I'll call delta y. Of course, to find the length of this part of the triangle, because we're trying to kind of move over to this next point, x1, y1, this length of this triangle here would be the initial point, x0, plus that change of x, that step that we took to move over to x1. And that's that first piece of Euler's formula that we wanted to find. To find the new x values that we're building, we're going to take the old x value before it and add to it the step that we're using. And again, it's going to be different in every problem. Okay, so how do we find the new y, which is y1? Well, I guess I could write it like this. We're not going to really ever write it this way, but the new y would be the old y plus the change of y. just like the new x was the old x plus the change of x. So of course the old y is just y0. But what is the change of y? That might not be as easy to see. Well, you'll notice the change of y over the change of x, because that slope is equal to dy dx, which is another way of saying slope. And if we treat this little delta x here in the bottom in our fraction as the denominator, we can multiply that to the other side. If I multiply that delta x to the other side, we can see that the change of y would be the derivative dy dx, of course evaluated at x0, y0, times delta x. And that's the key. We're going to increase y0 by that change of y, and that change of y is dy dx times the change of x. Okay, once we realize that, we can actually write out the y component of our new point. To find the new y value, we'll take the old one, of course, and add to that the change of y. This entire thing here is one term, which is the change of y. And that's actually key. In terms of the order of operations, we would have to multiply dy dx times delta x, and then add that to the old y. So be careful with that order of operations. It's a very common mistake. And there we go. That defines the new point x1, y1. And now we're building this piecewise function that kind of starts looking like the exact or the original equation. And then we just kind of repeat that. We're going to use that new point x1, y1 to find the next point x2, y2. And to do that, we'll just repeat steps 2 and 3. How many steps do you take, or how many times do you do this? Well, again, every problem's different, but in general, it's usually just a couple times. So I'm going to go ahead and do that again. If you're able to kind of fit in this next step in terms of the graph and the details, please do, but maybe you just want to see how to do the next step one more time. So let's go over to x2, y2. Again, we're taking that little step, which is delta x, over, but to find the slope, now we're going to do the derivative evaluated at x1, y1, so that we can figure out what that next point will be. Again, there's a change of x and a change of y. That change of x is the old x, but now it's x1 plus our step size, delta x. To find the change of y, it's still the derivative times delta x, but again, the derivative at x1, y1, not the x0, y0. Ultimately, just realize that this is what is called a recursive algorithm, because a set of steps are repeated with the previous answer in the next repetition. So we're taking the answer we're getting before and using it again to figure out a new step. Each of these repetitions we call an iteration. So this formula right here to find that y value is really the main component of Euler's formula that you're going to want to memorize. This formula right here, hopefully it'll just become something that you know, but ultimately if you can memorize it and apply it, you'll do Euler's formula hopefully with no issues. So just kind of realize that many differential equations can't be solved analytically, but we can certainly find an approximation, and that method we're going to use again is Eulers Method. So if we can't separate our differential equation, this is kind of the next best thing we can do, unless for some reason we're looking at a slope field and using that to analyze our differential equation. So Euler's Method, again, just to repeat so you know what this is used for, is used to estimate an original function, a particular solution, from the differential equation. We're actually going to get some numbers, again, compared to 6.2, where we're just looking at the slope fields and kind of seeing what was happening. So what you need to realize, and it concerns really memorizing Euler's Method, is that it's just a glorified tangent line approximation with multiple approximations that we're kind of connecting, so to speak. And the way I can prove that to you is just kind of recall our tangent line formula that we were using, point slope form, y minus y1 equals m times x minus x1. Normally, I told you all when you were doing these problems for tangent line approximations to not simplify. For the purposes of comparing this to Euler's method, I'm just going to move over that y1 by adding it. Usually we probably would put that y1 at the end of the line, but I'm going to put it first. So it's going to be y1 plus m times x minus x1. So why is Euler's method just a glorified tangent line approximation? Well, if you take a look at Euler's method, everything kind of lines up when you compare these two equations. One we've already known for a while now, the tangent line approximation or point-slope form. But now this new Euler's method, why are these two essentially the same? Well, you'll notice y1 is just a y value, and in our Euler's formula we're calling that the old y value. Of course, m in our tangent line equation is a slope, and a slope, of course, is another way of saying dy dx or a derivative. And another way of saying 1x minus another x is a change of x. So I hope you're not looking at Euler's method as some weird formula that doesn't really make sense. It really just is point-slope form, or the tangent line approximation equation that we've been using all along. Because of that, we also need to kind of remind ourselves about the error concerning tangent line approximations, because it also will apply here. Recall that if your graph is concave up, like in that last slide you saw, then your tangent lines would be below the curve, which would mean the approximation is an under-approximation. If you flip that and say that the graph is concave down, then that would, of course, make your approximation an overestimation or an over-approximation. Okay, I'm going to spend these next two slides looking at this one problem using Euler's method. And the reason we're going to start off with this problem is because it's a problem we can do without Euler's method. This problem we could actually do without having to approximate it. Just as a quick aside here, the derivative dy dx, which is equal to 2x, that original equation would be x squared plus c. And of course we could plug in our point and find the plus c, and that's nice and simple. But I'm going to use this Euler's method on a problem that we don't need it on necessarily, just to kind of compare the two methods, where we can actually solve it by separating or applying Euler's method to approximate it. And I'm also going to give you a visual to kind of tie all this stuff together. So let's go ahead and start. We have to start at the point we're given, so our x0, y0, of course, is 0, 1 from above right here. So, as a reminder, our two equations are this. To find the new x value, it's the old x plus the change of x. To find the new y value, we have our Euler's method. And again, be very careful in terms of order of operations. All of this is our change of y, so all that needs to be done together, and then we add the old y, y0. So what is our step size? How much are we moving over each new step we take? Well, here it's 0.5. So to find our new x value, we'll take the old x value of 0, and add to it our change of x, our step size of 0.5. So our new x value is 0.5. Also note over in our picture, I plotted our initial point, 0, 1, right here. We're going to start plotting all these points and connecting them to see what this piecewise function graph, how that compares to the true graph. Okay, so how do we find the new y value, y1? Well, we're going to take the old y value, which is 1, and add to that the derivative, which is 2x, evaluated at our point 0, 1, times our change of x, which is 0.5. And again, I need to emphasize that all of this needs to be done together first before we add 1. So the good news about our derivative is it only has x's in it, so we can of course just plug in the 0 of x and evaluate that. That all becomes 0, and of course when we add 1, our new y value is 1. So the next point in our journey along this piecewise function is at the point 0.5, 1. So I'm going to go ahead and plot that on our graph over here to the right, and connect that with a straight line, because again, this is a linear piecewise function that we're building. Okay, so to find the new x value, x2, I'm going to take the old x value, which is 0.5, and add to it the step, which is 0.5. 0.5 plus 0.5 is 1. To find our new y value, again, we take the old y value, not from the step before, but from the step we're on. So our old value, y value, is 1 here. And then we're going to add to that the derivative evaluated at our point 0.5, 1, times the step size of 0.5, which now means we need to take that point and plug it into our derivative. If you take the point 0.5 and plug it in for x and evaluate this and add to it 1, you'll end up with 1.5. So that's the next point along our journey here. Our x2, y2 is 1, 1.5, and again, I'll plot that on our graph here. And you can kind of see what's happening here. We, of course, from before talked about that the solution to this differential equation was, of course, just x squared plus c. And you can kind of see this parabola shape kind of starting to take form. But let's keep on going. The next x value we're trying to get to will be the old x value, which is 1. And we're going to add to that the step size, or the delta x, of 0.5. So our new x value is 1.5. Our new y value is the old y value of 1.5. And to that, we're going to add the derivative evaluated at our old point, 1, 1.5, times our step of 0.5 a half. So we can take our point of x and plug it in, which is 1. So 2 times 1 times 0.5. Again, be careful. You have to evaluate all this in the brackets first, then add the 1.5. And when you do that, you'll get a y value of 2.5. So we can go ahead and call that our x3, y3, our new point, 1.5, 2.5. And again, I'll plot that on the graph to the right. And again, we're still seeing that parabola kind of shape. So something I didn't talk about at the beginning was, when do we stop? Well, if you notice from above, we're trying to approximate f of 2. And based on these steps we're taking, it's going to take 4 steps, because you'll notice, to find our x4, we're going to take the old x of 1.5 and add to it the step of 0.5. And of course, that gives us the x value we want to approximate of 2. So now we know we can stop. But of course, we got to find the new y value for that point. So we got to take the old y value of 2.5 and then add to that the derivative evaluated at our point times the change of x, or the step size. Again, what we need to do is take our point and plug it in, but since there's only x's in our derivative, we'll just plug in the x value of 1.5, evaluate first 2 times 1.5 times 0.5, and then add to that 2.5, and we'll end up with a y value of 4, and that's where we can stop. Using Euler's method, we just discovered that the approximation for our differential equation at 2 is equal to 4. Okay, so what does that mean? Well, now that we have this approximation using Euler's method, and here's a recap of that, f of 2 equals 4 from the last slide, and here's the graph that we had from the last slide. How does that compare to the value we actually could have found without having to do this approximation? So let's go ahead and solve this differential equation. Luckily, it's a very straightforward, easy one. If we move the dx to the other side and integrate both sides, we'll end up with y equals x squared plus c. And when we plug in our point 0, 1, we'll find a c value of 1. So we know the solution to this differential equation, or the original function, or the particular solution, is x squared plus 1. So of course, not a hard thing to do. If I wanted to find f of 2, I would just go ahead and plug in the value of 2 into our function. F of 2 would be 2 squared plus 1, or in other words, f of 2 is 5, which would be our exact value. So if we were to take that and graph it, of course, we're just looking at the graph to the right of 0 here. We're not going to draw the whole parabola. If I draw that parabola in, we know at the x value of 2, we have this dot up here at y equals 5. So our exact solution at the x value of 2 is equal to 5. But we just used Euler's approximation and found that the approximation was 4. And that should make perfect sense. Visually, it makes sense because, of course, you can see at 2, our Euler's approximation is giving us 4. But even more so, it should make sense because of the definition of error for these tangent line approximations. We know that our original function is concave up. So that must, of course, mean that the approximation is an under-approximation, which again, we can see visually, but you might not always have a visual. So seeing it visually hopefully will help you connect the fact that concavity tells us if the approximation is an under approximation or an over approximation. So there you go, a problem that we can do exactly and using Euler's approximation. So hopefully that gives you a good idea of how we can use Euler's approximation or Euler's method, and how that relates to solving a differential equation. Okay, in this last slide, let's do a problem where we have to use Euler's approximation. You'll notice our differential equation here is one we've talked about a little before, where we cannot separate this differential equation. So other than maybe taking a look at a slope field, there's really nothing we can do to analyze this differential equation until we know about Euler's formula or Euler's method, so we can approximate the original equation. And here we want to approximate the original function at 2. Okay, so one thing I think missing from here is the change of x, our step size. They don't outright tell us what it is. We kind of have to read between the lines here. They're telling us to start at 1 and end at 2 with 2 steps. So the only way to accomplish that, of course, is to have our step size or our change of x be 0.5. Okay, so let's get right to it. We're starting at our point, our initial condition of 1, 2, which is x0, y0. And again, as a reminder, here are our formulas for Euler's method. And again, be very careful that you analyze or you evaluate the derivative times the step size first, and then add the old y. Okay, so x1 is going to be the old x value, so 1 plus our step size of 0.5. So we're at x equals 1.5. To find our new y value, we need to take the old y value of 2 and add to it the derivative evaluated at our point times the step or the change of x. So in this case, we're going to have to plug in both x and y. So we're going to end up with 1 plus 2 times our step size of 0.5. And again, these brackets are important in the sense that we have to evaluate the brackets first, then add the 2. When you do that, you'll find a y value of 3.5. Got to go one more step so we can get to our x value of 2. So our x1, y1 is 1.5 comma 3.5. So to find our next x value, x2, we'll take the old x value of 1.5 and add to it our step size of 0.5. And that, of course, puts us where we wanted to end out. We want to approximate f of 2, so we're at the x value of 2 here, so we can stop after this step. So we need to find our new y value, the approximation for our function at 2. So we got to find that y value. We need to take the old y value of 3.5 and add to it the derivative evaluated at our point times the step size of 0.5. Again, our derivative has x's and y's in it, so we're going to have to take both x and y and plug it in. So it'll be 1.5 plus 3.5 times our step size of 0.5. Take all of that, evaluate it, then add 3.5, and we end up with a y value of 6. And that is our Euler's method approximation for this differential equation at x equals 2. Now we can talk about the error. How close or far was it? Well, we're not really going to know that since we can't separate this differential equation and actually solve it, but we can certainly talk about if it's an under approximation or an over approximation. And to do that, we need to look at concavity. And of course, concavity relates to a second derivative. So let's take the derivative of x plus y. The derivative of x is 1, and the derivative of y is 1. But we're taking the derivative with respect to x of a y term, so remember we need to throw in that dy dx. Okay, so 1 plus dy dx. That's really not our final second derivative in a sense if we want to write it in terms of x and y. We know dy dx is y plus x, so that's our second derivative. We need to figure out, is the graph concave up or concave down at the point in question? The point in question you found from before was 2, 6. So that's the point we have to plug in. So I think that's the one thing you're going to have to be careful with. There's several points you could have plugged in, but remember, we want to know, is the approximation an over approximation or an under approximation? So that has to be done at the x value where we're making the approximation. In this case, it's 2 comma 6. Okay, so let's plug in our point 2 comma 6, and of course the math is nice and easy here. We end up with 9. Don't really care so much that it's the value of 9, we care more that it's a positive value. And we know a positive second derivative means our graph is concave up. And if our graph is concave up, that means our tangent lines are below the curve, which ultimately translates to mean that our approximation is an underestimation. And the reason for that is because the graph of the solution is concave up. This next little bit to round out this slide is just some extra information. You don't have to worry about knowing how to do this in your calculator, but just to give you an idea of what the exact value is. If you were to use a calculator, and I haven't ever really talked about these steps, and you don't need to know these steps, but if you were to use a calculator to get the exact value for this differential equation at 2, it actually turns out to be 7.873. Again, don't be so concerned with how I got the number. I just want to put that there just so you can compare the approximation to the exact value. And at least we can appreciate that we were right concerning the approximation being over or under. The approximation is definitely under our exact value, so at least we can check it in that regard. And then it's also maybe just interesting to see how close our approximation is. It's not very close, but again, we're not always concerned with that. We're just concerned with, is it an over approximation or an under approximation?